perform visit action. Yeah, I agree with that. Okay, so this is slightly different. The first thing we do is we perform our visit action, whether that's printing out something or whatever. Okay, then if that's the first thing we do, then we only have two more things to do, and that is to ask if n has a left child, then we recursively call the same algorithm on the left child. And really crucial here, okay, notice that it's if and then if, okay? It's not if else. If it was if else, our branching factor of our algorithm would just be 1. Okay, it would look like in code there was 2 recursive calls, but it really would just mean there's 1 based off the condition. These are 2 independent branches of recursion, okay? And again, we need that because we have binary trees, so we always have 2 possible options. And we have preorder on the right child. Again, that's it. That's all you need to traverse this particular tree. Okay, I'll not bother with stack frame this time, but you can, if you wish to work through that yourself, you can. Okay, so the first thing we do then, I also asked, why did we visit action directly for this type of tree? Okay, so there's 3 traversals, and I will give you, the next couple of slides will have the actual examples associated with the actual traversals, and we'll talk about that. So hold that thought for just a couple of seconds. Okay, so if we perform the visit action first, and we're starting here, if this is the root of our tree, we'll call it n. So then we start at the root, okay? The first thing we meet, we present, or we print, or do whatever the visit action is. Then we ask the question, is there a left child? And in this case, there is. Okay, so then we move to that left child. Again, it's in order, so we come back here and we do the visit action first. Okay, so we do the visit action, and then we ask, do you have a left child? Which it does. So then we come down here. Okay, again, same idea. We ask the first question we ask, is there, well, it's not a question, it's a statement, do the visit action. Okay, then ask, do you have a left child? Nope. Do you have a right child? Nope. Okay, then you collapse that method call and go back to the previous call. Right now in this previous call, we have done the visit action and we have done the left child recursion. So now we recurse down the right side. Okay, so do you have a right child? Yes. Okay, so then we move down here and we perform the 4th visit action. Okay. We ask then, is there a left child? There is. So then we come down here, perform the 5th visit action. That's the first thing we do. Is there a left child? Nope. Is there a right child? Nope. Okay, then that method will close and will collapse back to the previous one. And at this point in time, we've done the first 2 things. So then we do finally ask, is there a right child? Which there is. So then we come down here. So now the 6th action, there's no left child, there's no right child. So then we come back here. There's nothing left to do. We've done all 3 parts of the algorithm. Then that collapses back to the calling one. Again, we've done all 3 parts of this particular call, and then we collapse back here. Okay, we've done the first 2 parts. We've done the visit action, we've done the left child traversal. So now we go down the right side. Okay, ask the question, is there a right child? Yes. Come down here. Then we do the next visit action. We're up to 7 at this point in time. And is there a left child? Yes, there is. Come down this side. 8th visit action, no left child, no right child, collapse to the previous call. We've done the first 2 parts. Then we do is there a right child? There is. Come down this side, do the visit action, and no left child, no right child, collapse back here, and collapse back here, and we complete the traversal. Okay, and we can see that just by following this recursive calling, we can traverse around every single node in the tree. And this guarantees that we will meet all of the nodes and perform the visit action. Okay,